Every clock you have ever heard, a grandfather clock in a hallway, a cathedral bell tower, a pocket watch in a waistcoat, makes the same sound. Tick-tock. That rhythm isn't decorative, it's not an accident of the gears. It is the sound of a physical problem being solved 60 times a minute, without pause, for 300 years. Every clock is powered by stored energy, a falling weight or a coiled spring that wants to release itself all at once, as fast as possible. The escapement's job is to stop that, to meter it, to release it in exactly equal steps of time. By the 1600s, clockmakers had built mechanical clocks that worked, but every one of them drifted, gaining or losing minutes every single hour, because the escapement at the heart of each clock was not metering those steps equally. Around 1670, a mechanism appeared in London that changed that. The clock it produced was accurate to within seconds per day, roughly 10 times better than anything built before. Its inventor is disputed. William Clement and Robert Hooke both have claims to the mechanism. What is not disputed is what this mechanism was and exactly why it worked. The device every clock used before this had a fundamental flaw buried in its geometry, and for 300 years, every clockmaker had accepted it as the cost of doing business, until someone changed the shape.
The Verge escapement works like this. A vertical toothed wheel, the crown wheel, meshes with two small paddles, called pallets, mounted on a central rod. As the rod rocks left and right, each pallet catches and releases one tooth in turn. The pendulum is attached to this same rod. One swing, one tooth. It's mechanically elegant, and it worked, after a fashion. But here is what the geometry forces upon you. For the pallets to catch and release the crown wheel's teeth, the rod must rotate far enough for each pallet to fully engage and clear. The pendulum attached to it has to swing through a wide arc, 80 to 100 degrees side to side. That's not a design choice. That's geometry forcing the pendulum's hand. And here is the fatal physics. Galileo had proved it. A pendulum's period, the time for one full swing, is only truly constant when the arc is small. At large angles, the period depends on amplitude. Swing harder, it takes longer. Swing softer, it ticks faster. The Verge forced the pendulum into the zone where this matters. This means the Verge escapement was in a permanent war with itself. Any change in the mainspring's force changed the arc, which changed the period, which changed the timekeeping. The spring wound tight in the morning runs faster than the spring half spent by evening. You could regulate it, you could not fix it. The chain of failure is locked in. The pallet geometry demands a wide arc. The wide arc makes the period variable. The variable period makes the clock drift. Clockmakers had spent 300 years compensating for this. No one had removed the cause. In 1637, Galileo had sketched an escapement that addressed the problem, a flat wheel with face-mounted pins instead of a rim-toothed crown wheel. His design would have allowed a longer, slower pendulum, one less disturbed by the escapement, one whose natural frequency could dominate the mechanism. Galileo understood the physics precisely. He died before the mechanism was built. His son attempted construction from the drawings. It was never finished. In 1659, Christian Huygens approached the problem with mathematics. He proved that a pendulum following a cycloidal path, a specific curve traced by a rolling circle, would have a constant period regardless of amplitude. His solution? Add curved metal guides to the pendulum pivot, forcing the cord to wrap around them as the bob swings wide. This changed the effective pendulum length to compensate for the amplitude. The physics was correct. At the contact zone between the cord and the cheek, the effective length shortens precisely as the amplitude increases, and the two effects cancel out. In theory, perfectly. But the cheeks had to be machined to a precise cycloidal curve. That curve changes its exact shape depending on the precise length of the pendulum beneath it. One small error in the metalwork, a fraction of a millimeter, and the compensation failed. In 1659, that level of consistent machining precision was beyond reliable production. Huygens' solution was theoretically perfect and practically fragile. Clockmakers also tried simply shortening the Verge pallets. Smaller paddles, smaller required arc. It reduced the error, but the crown wheel's geometry imposed a hard floor. Below a certain arc, the pallets could no longer clear the teeth on the release stroke. The mechanism seized. You had hit the geometric limit of the crown wheel design itself. Every approach had a reason it didn't reach production. Galileo's? Unbuilt. Huygens? Too precise to manufacture consistently. Shortened pallets? Blocked by the crown wheel geometry itself. The gap between 60 degrees and 6 degrees was still open. Here's what's strange. The solution wasn't a smaller or better version of what already existed. It required abandoning the crown wheel entirely and starting from a completely different geometry.
The first change: replace the vertically mounted crown wheel with a flat horizontal escape wheel, a wheel with forward-angled teeth around its rim. This one geometry change removed the hard floor on the arc. The second change: replace the straight verge rod with an anchor-shaped lever. Two pallets, curved to match the escape wheel's tooth geometry, arranged at roughly 100 degrees, like a ship's anchor pivoting on its crown. This shape is why the mechanism carries the name it does. The anchor's curved pallets engage each escape wheel tooth at a dramatically shallower angle. The pendulum only needs to swing through 4 to 6 degrees, total, side to side, to complete the catch and release cycle. That's the zone where the pendulum's period is genuinely constant. One shape, one geometry change, closing the 300-year gap between 80 degrees and 6. If you want to understand more of these, the mechanisms behind the objects you've taken for granted your whole life, subscribe. Here is the full mechanism, one step at a time. The pendulum hangs at center. Both pallets are clear of the escape wheel. No tooth is being held. The spring's energy is blocked only by the inertia of the system. The pendulum swings left. The entry pallet drops onto a tooth of the escape wheel. The wheel stops dead. Every tooth behind it is locked. At the moment of contact, the tooth pushes back against the curved impulse face of the pallet, nudging the anchor, and with it, the pendulum, fractionally backward. This is called the recoil. That recoil is not a flaw, it's a feature. The tooth's backward push adds a tiny pulse of energy to the pendulum at each catch, just enough to compensate for air resistance and friction. The escapement sustains the pendulum swing without a separate impulse mechanism. The recoil does that job. As the pendulum swings back toward center, the entry pallet slides off its tooth. The escape wheel advances, exactly one tooth, no more. The spring releases one increment of energy, no more than that. The pendulum continues right. The exit pallet catches the next tooth. The wheel stops again. One half swing, one tooth advanced. The same recoil repeats on the exit side. The tooth pushes back, the anchor nudges left, the pendulum receives its energy input for the return swing. The mechanism is perfectly symmetrical. The pendulum returns to center. The exit pallet releases. Another tooth advances. One complete pendulum swing, left and right, has advanced the escape wheel exactly 2 teeth, every time, without variation. A standard anchor escape wheel has 30 teeth, 2 advance per pendulum swing. With a seconds pendulum, 1 full swing per second, the escape wheel completes 1 rotation every 15 seconds. The gear train above it translates that rate into minutes and hours. Every tooth, every second, every minute, mechanically counted. Each pallet does 2 jobs with 2 different surfaces. The locking face arrests the escape wheel. The impulse face receives the recoil push from the tooth, converting that backward nudge into forward energy for the pendulum. 2 functions, 1 piece of curved steel. Compare the numbers. The Verge ran at 80 to 100 degrees, squarely in the zone where the pendulum's period changes with amplitude. The Anchor runs at 4 to 6 degrees, where the period is effectively constant. The result? From 2 minutes of drift per hour to 10 seconds per day, a 12-fold improvement. From a clock that tells you the approximate hour to one that tells you the precise minute. Within years of the Anchor's introduction, the long pendulum clock, the grandfather clock, became possible. A pendulum long enough to swing in exactly 1 second could now run with an escapement that demanded only a tiny arc. The clock's size was no longer a compromise, it was a design choice. Clocks that had previously been instruments of approximation became instruments of measurement. The anchor escapement had not just improved a device, it had changed what a clock was. So the pendulum held its arc. The seconds were equal. But what the anchor escapement actually made possible, that's not a story about clockwork. It's a story about what happens when you can measure time precisely for the very first time in history. In 1675, King Charles II founded the Royal Observatory at Greenwich, specifically to solve the longitude problem. Ships crossing open ocean were dying because navigators couldn't calculate their east-west position. The solution required comparing local time to a reference time, which required an accurate clock. The observatory's first task was building tables of astronomical positions, where every star and planet would appear at every hour for years ahead. Those tables were calibrated against the observatory's pendulum clocks. If the clocks drifted, the tables were wrong. If the tables were wrong, ships died. At sea, 4 seconds of clock error translates to 1 nautical mile of position error, the margin between a harbor entrance and the reef beside it. The anchor escapement made pendulum clocks accurate enough to serve as the observatory's standard reference, the clocks everything else was measured against. Every astronomical table used by every navigator from the late 17th century forward was calibrated against anchor escapement clocks at Greenwich. Every position fix, every safe landfall, built on the escapement holding its seconds. In laboratories, the same accuracy enabled physicists to time experiments that required seconds-level precision for the first time. One of the first things they measured? Pendulum swing rates at different latitudes. And in those measurements, they detected a fact nobody had proved, that the Earth is not a perfect sphere. It bulges slightly at the equator. A century later, in factories and railway stations, the anchor escapement's legacy had scaled beyond any one institution. Synchronized time meant coordinated shifts, railway timetables, schedules. The anchor escapement didn't just improve clocks, it made time a shared, measurable resource, available to everyone. Every factory shift ever scheduled, every railway timetable ever printed, every star position ever measured. All of it was built on the anchor holding a pendulum to a 6-degree arc. The anchor escapement was the first mechanism in history to use a stable, natural oscillator, the pendulum, to control a counter. Every quartz clock, every electronic timer, every microprocessor on Earth uses the same principle. A stable frequency reference, an oscillator, equals steps of time. The physics is identical. The material is silicone instead of steel. The GPS receiver tracking your position right now is accurate to within meters because it uses a crystal oscillator controlled by the same logic Clement used in 1670. A stable oscillator, a counter, equal steps of time. The next time you hear a clock tick, that sound is 350 years old. It's the anchor catching a tooth, releasing it, and catching the next one. One step at a time. The same shape, the same physics, still ticking.